Hello and welcome back to the course on artificial intelligence. In today's section, we're tackling the topic of deep Q learning. So let's see how we're going to attack this. In this section, we will learn a deep Q learning intuition, the learning side of things. So we're going to separate deep Q learning, the intuition behind it, into two parts, the learning and the acting. And we're going to have two tutorials on that. So first we'll understand how the neural networks actually learn and how they update their weights based on what we are feeding them in and how the whole concept of Q learning works. So how we're going to take the temporal difference concepts that we discuss in simple Q learning, we're going to apply them into deep Q learning. And then we're going to talk about how deep Q learning algorithms actually decide what action to take in what states. Then we're going to talk about experience replay, a very important addition on top of deep Q learning, which actually enables deep Q learning to work properly, and you'll see why it's important from that tutorial. And then we're going to talk about action selection policies. We're going to talk about how deep Q learning agents are able to combine exploration with exploitation. So once they found something, a good approach, they can use that approach, but also they need to explore so that they don't get stuck in a local maximum. And one more thing I wanted to mention about this section is it is highly beneficial if you have a look at Annex number 1, artificial neural networks. So if you go and explore all those topics, we've got some very powerful intuition tutorials prepared for you there. If you haven't done the deep learning course, if you've done the deep learning course, then you already know all of these things and you can proceed with the section. But if you want to get that additional knowledge about neural networks before you proceed with this part of the course, this is highly advisable because it will help you understand exactly how neural networks work and why they're so powerful, why we're leveraging them in this deep Q learning algorithm. And once you've refreshed your knowledge or gained that knowledge on neural networks from that annex, then come back here and we will proceed with the deep Q learning. If you're pretty comfortable with neural networks, then let's get straight into it. Let's start talking about deep Q learning intuition. And I look forward to seeing you on the first tutorial. Until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. And finally, we're on to the fun stuff. We're on to deep Q learning. All right, so let's have a look. Previously, we spoke about Q learning and what it's all about. And we learned about the agent, the environment, and how the agent will look at the state he or she is in, take an action, get a reward, enter into a new state. And based on that feedback loop, they will continue taking actions and they'll learn from that, understand what are the better actions to take. And so we looked at this basic example of a maze. We understood that as the agent explores the environment, it understands what the values of the states are. Then we moved on from dealing with the values of the states to dealing with the values of the actions or the Q values. And then based on that, we understood how plans in non-stochastic environments work and how policies work in stochastic environments. And this is an example of a policy. So that's a quick recap of everything we discussed in the basic Q learning. And now let's have a look at how this can be taken to the next level through deep learning, through adding deep learning. Okay, so this is our environment. And what we're going to do now is we're going to add, instead of just doing basic calculations in this matrix that we have, which is pretty simple, what we're going to do is we're going to add two axes. We're going to add an X and Y axis, or we'll call them X1 and X2, just to make things even more general. And here we've got we'll number the columns 1, 2, 3, 4. Here we'll number the rows 1, 2, 3. And so now every single state can be described by a pair of two values, x1 and x2. So any one of these squares in which the agent can possibly be in can be described by x1, x2. So for instance, right now he's in the square with x1 equal to 1 and x2 equal to 2. And therefore, that's in that same way, we can describe any square, meaning we can describe any state. And of course, this is a very simplified version of an environment of describing states, but nevertheless, it works in this case. And that means that now we can feed these states into a neural network. And by the way, here, I would just like to mention that at the end of the course, we've got annexes. We've got annex number 1 and annex number 2. In order to proceed successfully with this section, it's highly advisable that you check out annex number 1, which is on artificial neural networks, so you understand how they work, so that we don't have to delve into that here, and we can just use the benefits of the knowledge of how artificial neural networks work. And so we feed in this information on the state into a neural network, and then it will process this information, so x1 and x2. Depending on the structure of the neural network, it might have multiple hidden layers and so on. So that's something that you'll figure out in the practical tutorials. But at the end, we will structure in such a way that it spits out 4 values. And these 4 values are actually going to be our Q values. So the values which dictate which action we need to take. And further down in this tutorial, we'll see exactly how these Q values are used to decide which action is taken. But the main point here is that we no longer look at just this maze from a Q-learning perspective. We're now taking the states of the maze and we're feeding them into a deep neural network in order to get these Q values. And at the end of the day, we're still going to come up with an action. We're still going to understand what action we need to take, and we'll discuss all this in more detail. But the question right now is why? Why are we doing all of this? Why are we making things so much more complicated when that initial approach of Q-learning was working already? Well, the reason for that is the Q-learning was working in this very simplistic environment. And we're continuing to deal for now with this very simplistic environment in order to better understand the concepts. But at the same time, that simple Q-learning will no longer work in more complex environments. And we're talking about, for instance, the self-driving cars, which you'll be creating, or playing Doom, when the artificial intelligence is playing Doom, or other Atari games like Breakout, or even self-driving cars and more advanced reinforcement learning things such as like robots walking around and performing actions. In all those cases, basic Q-learning is insufficient, is not strong, is not powerful enough to be able to master those challenges. And just like we've seen in the deep learning course, if you've been in our deep learning course, or if you've done the annex sections, annex number 1 and annex 2, you will already know that deep learning is by far superior to any type of machine learning, let alone simple Q-learning. And that's why we're leveraging the power of deep learning here. So we're feeding in the information about the environment as a vector of values, so in this case just 2 values, into a deep neural network, and then we're using that to perform the actions that we want to decide which actions the agent's going to take. So that's kind of like a high-level overview of why we're doing this. And now let's have a look at, in a bit more detail, at what happens to the concepts of Q-learning when we make this transition from simple Q-learning into deep Q-learning. So as you saw in the previous intuition tutorials, we had a slide like this, which is the foundation of temporal difference learning. This is the formula for temporal difference. And basically, so let's go through this. So basically, we had an agent who was in this state over here, which is indicated by blue arrow. And we were understanding how temporal difference works for this Q value of, for instance, going up. And so what we saw here was before, this is in the simple Q-learning, not the deep Q-learning, this is in the simple Q-learning. What we saw was before, the agent had a certain Q value that he had learned about this action of going up. And so then he decides to take this action to go up. And right after he takes this action, he gets a reward for taking this action in this state. And that is that reward. Plus, now he can evaluate the value of the current state he's in, which is the maximum of all of the new Q values of all of the Q values of the new actions he can take, A prime, in the new state S prime. And we multiply it by the decay factor of gamma. So that is essentially the new Q value, or kind of like the empirical Q value that he has just received for taking that action. And ideally, these two should be the same. So the Q value that he had in his memory about this action in this state, it should equate to the actual reward plus the gamma times the value of the state that he ended up in. And therefore, that's how we calculate the temporal difference. We take what he got after minus what he had in mind, what he was expecting. You subtract one from the other, and that's your temporal difference. And then you use your learning rate alpha to adjust your Q value, your new Q value by the temporal difference, but with a coefficient of alpha. So that is the essence of the simple Q learning. Now let's have a look at how it changes in deep Q learning. And so we're still going to work with this slide, but we're going to just see exactly what's happening. So in deep Q learning, the neural network will predict 4 values. As we saw in the previous slide, and as we'll see further down in this tutorial, the neural network will predict 4 values, or it might predict more values if there's more possible actions in a given state. But in this case, we know that there's only 4 actions: up, right, left, or down. And so the neural network will predict 4 of these values. So there will be no, in a deep Q-learning situation, it's important to understand there's no before or after. And this is how we'll get to know this a bit better. So the neural network will predict 4 of these values. And it will compare not to what will happen after, but the neural network will compare to this exact value, but it was this value which was calculated in the previous step. So in the previous time when the agent was in this exact square, so let's say, I don't know, some time ago, the agent was in this exact square as well, and it calculated this value previously. So in the previous time, a long time ago, the agent calculated this value. Then the agent stored this value for the future. And now the future has come. So now he's in the square again. And now he's got these Q values, which is predicted. And one of them is for going up. So now what he's going to do, he's going to compare the predicted value of Q to this value which he had recorded from the previous time. And we'll understand exactly why this is important right now. So just important to understand here is there's no before and after in this specific square, this specific time. We're taking the Q value that he's predicted using the neural network this time, and we're comparing it to this value, which he had from the previous time. From the previous time he was in this square, assessing all of the situation. And, the previous time he actually performed this action. So there we go. Now let's have a look at how this all works out in the neural network and why is it like that. I know it sounds a bit complicated right now, but we'll break it down into simple terms right just in a second. So this is our neural network. We're feeding in the states of the environment into the neural network. It's going through the hidden layers. Then it's coming out with these outputs, Q1, Q2, Q3, Q4. In that specific state, these are the Q values that the neural network is predicting for the possible actions. Those are the Q values. So then we're comparing to target. And these targets is exactly, so if we go back here, this is the target. So this is the value that was predicted. And then, but also we know that we have a target from the last time we were in the square. We have a target for this same action, which is up, for instance. So here we've got a target and we're going to compare. So we're comparing Q1 versus that target. We're comparing Q2 versus that target, the target that we had from previously. Q3 versus the target, Q4 versus the target. And so this is the part where the neural network or the agent is now learning through deep learning how to better go through this maze. And the key point here is that we're still applying Q-learning, but the concepts in simple Q-learning, you learn through temporal differences, which are pretty straightforward, which we've already discussed and we know quite well by now. But at the same time, in deep learning, how do neural networks learn? Well, neural networks learn through adjusting their weights. So we have to adapt the concepts of simple Q-learning to the way neural networks actually work, and that is through updating their weights. And so this is what we're trying to figure out here. How do we adapt that concept of temporal difference to a neural network so that we can leverage the full power of neural networks? And so far we've gotten this. So we enter our environment state here as a vector, goes through a neural network, we get predictions of Q values, and then from the previous time the agent was in that state, we have these Q target 1, 2, 3, and 4 for each of these respective actions. And so now we're up to, okay, let's compare each one with each one. And from here, it becomes pretty straightforward if you're up to speed with neural networks. Once again, that's all in annex number 1. We're going to calculate a loss, which is L here, and we're going to be Q target, this one, minus Q, minus this one. We're going to square that, so the square difference of each one of these, and we're going to sum them. So we're going to take the sum of the squared differences of these Q values and their targets, and we're going to sum them up, and that's going to be our loss. And so ideally, just as we had in the temporal difference learning, so if we go back for a second, remember we said ideally we want this to be equal to this. So we want the temporal difference to be 0. So that means basically the agent is predicting exactly correctly what, the Q values that the agent is predicting are exactly, or that he has in memory, are exactly descriptive of the environment, and therefore the agent can navigate the environment pretty well, right? There's no surprises. There's no if as long as this temporal difference is highly positive or highly negative, then we've got some surprises. But if the temporal difference is 0, then he knows the environment so well that he can predict what's going on, and therefore his policy is going to be very good, and he's going to be able to navigate it. So here, same thing. So we want this loss to be as close to 0 as possible, as small as possible, and that's why now this is the part where we are going to leverage the real true power of neural networks. So we're going to take this loss and we're going to use backpropagation or stochastic gradient descent to take this loss and pass it through the network. Pass it back or backpropagate it through a network, and through stochastic gradient descent, update the weights of these synapses in the network, so that next time we go through this network, the weights are already a bit better descriptive of the environment. And that's exactly how it works. So here you have, if we go back, this is calculated, loss is calculated, and it gets propagated for the network. The weights are updated. Then the next time we get here, this happens again. And we get here, this happens again, and so on. And it keeps happening, and that's how this agent learns, or basically now it's a neural network, which is the brain of the agent, is learning, is becoming more and more descriptive of the environment, and therefore the agent is able to navigate the environment better. When we say descriptive environment, basically means that when we put in the states of the environment that the agent is in, we are more likely to get closer and closer to the actual Q values. And that happens because the Q values that we want and find the right action. And that happens because these Q targets are actually empirically derived. So how does he find these Q targets? That's actually this. So he actually observes, okay, so once I do take this step, what's the reward I get? And then what's the value of this state? So same thing as we saw previously in Q learning, in the simple Q learning intuition. So he learns this through trial and error, and then he constructs his network or updates the weights of his network in such a way that the predicted Q values are closer and closer approximating the target Q values. So very similar to the concept we discussed here in the simple temporal difference learning of the simple Q learning algorithm. So there we go. That's how the agent learns. So we're up to here. That's the learning part. Hello and welcome back to the course on AI. In the previous part, we talked about the deep learning, Q learning intuition. We started there, and in fact, we actually got all the way to this part, and where we talked about learning. And now we're going to move on to the actual acting part. So there's two distinct parts that we have to remember. So that's the learning part, but now he's done all of this. That's beautiful. Now he actually has to take an action. He has to decide what is he going to do. He's going to do action 1, 2, 3, or 4. And so how does he do that? Well, the way he does it is now, given those same Q values, so the Q values don't change. After we have these Q values, we've compared them, we've calculated the loss, we've backpropagated the error, we've updated the weights, but the Q values don't change in that whole process. So after we've got the Q values, they're fixed. We know what they are, so all of this happens, the network's updated, and now using those same Q values that we had, what we're going to do is we're going to pass them through a softmax function. And again, softmax is described in Annex 2, and we'll talk a bit more about softmax further down or we'll talk about this action selection policy further down in the rest of this section, so just in a few tutorials. But for now, we're just going to say we're passing it through a softmax function, and basically what it does is it helps select the best one. It selects the best action possible. There's a small caveat to that. It's not just the best one possible. We'll talk about that in the action selection policy tutorial. But for now, let's just say it selects the best action from here. It says, okay, so Q1, the likelihood, basically we know the Q values. So it's predicted the Q values, so it can look at them and say, okay, so the highest Q value out of these, just as we did in the simple Q learning algorithm, it'll just look at all these 4, say the highest Q value is this one, and I'm going to select that action. I'm not going to take those. And that's pretty much it. That's how it chooses which action takes the action, and then all of this process happens again for the next state the agent ends up in our case, in the next square of the maze. But generally speaking, it's the next state. So there we go. That's how we feed in a reinforcement learning problem into a neural network through a vector describing the state that we're in. And once we feed it in, there's two parts of the process that happen. Part one is the learning. So remember that part where we compare each of the Q values with the targets, and then we backpropagate the loss through the network to update the weights so that our network is learning as we go through this maze or through this environment. And also the second part is, of course, we have to act, we have to select an action, and that is where we pass the Q values through the Softmax function, or basically an action selection policy, which we'll talk about further down, and then we simply select the action that we want to take and we perform that action, and then this whole process starts again. And then maybe the agent gets to the end, maybe the agent doesn't pass the game. In any case, the game ends, and then once again the whole process repeats. The agent plays the whole game again, and then that stops. So basically that's another epoch. Every time the agent, every time the game ends, whether favorably or unfavorably, that's the end of an epoch, and then he starts again, and then he starts again, and then he starts again, and so on. So that happens, and this process happens for every single time the agent is in a new state. So the state is encoded here. So that's important. So not just for every single game that he plays, but for every single state. So he's in a state, it goes through this process, updates, and so on, and happens every single time. And so the learning happens, and then the acting happens as well. So that is deep Q learning or the intuition behind deep Q learning. We've got lots more to cover off. And then, of course, we've got the practical. And in the meantime, if you'd like to get some additional information on deep Q learning, we've got a recommended reading. So we've already spoken about Arthur Giuliani's series of blog posts. If you look at simple reinforcement learning with TensorFlow Part 4, you will find the part that's relevant to what we discussed today. Note that here he talks about convolutions. We are not covering convolutions in this section. We're going to be talking about them in the next section of the course. So the difference here is that, so just kind of skip the convolutions part for now, and we'll talk about them in the next part of the course. But the difference is in convolutions, you're like your agent is looking at the image, and therefore he has to process an image, so an additional complication. For now, we're slowly, gradually building up to that. For now, we're encoding our environment through, so if you look here, we're encoding our environment, or maybe look at this one probably, encoding our environment or encoding a state the agent is in as a vector. So in our case, it was a very simple vector of two values. Sometimes people, even in that simple maze, sometimes, or as you'll see from this blog post, sometimes people prefer the one hot encoded version of that state. So basically where every single box of the maze has so you have like a vector of, in our case, it would be 12 values, 3 by 4. So it's like either 1 or a 0, depending on which element, in which box you're in the environment. So in whichever way you decide to encode your environment and the state of your environment, that's how we're encoding it. So it's basically a vector. The key here is that it's not a convolution, so it's not like an image and there's no convolution involved. So this part will come later. For us, it starts over here, and that just simplifies the process for us to gradually understand better. And of course, don't forget that this blog post is written in TensorFlow, and we're using PyTorch in our tutorials. So hopefully you enjoyed this quick intro into deep convolutional deep Q learning. And on that note, I look forward to seeing you next time. And until then, enjoy artificial intelligence. Hello and welcome back to the course on artificial intelligence. All right, so I hope you're enjoying the tutorial so far. We're nearly done with the intuition. You'll very soon get to the practical side of things. We've just got a few little things that we need to cover off. All right, so previously we talked about how we add neural networks into this whole equation of Q learning and take Q learning to the next step and turn it into deep Q learning. And today we're going to add an extra important feature which you will be coding in the practical side of things. So Hadlan and I decided that it's important for us to cover it off in the intuition side of things so that you're more prepared for it when it comes in the coding side of things. So as we discussed, we've got the network there. There's two parts that happen. First of all, it's the learning. So the network actually learns with every new state. It slowly updates its weights to get better and better and better at dealing with this environment. And then there is the acting inside the state. So after the Q values have been counted in the state, then one Q value is selected. So today we're still going to talk about the learning part. We're going to come up with a interesting feature that's going to, well, we're not going to come up with this feature ourselves, but we'll talk about a feature that is very important for deep Q learning, and that feature is called experience replay. All right, so here is our network. So we've just copied it over here. We've got that loss that is calculated at the bottom is back propagated through the network. And let's have a look at an example of what happens to understand the problem that we're dealing with a bit better. So here is an example actually from this course. This is a screenshot exactly from this course. This is what you'll be programming. This is a self-driving car that is driving through this along this road, and it has to learn how to navigate this road. And so what is, as we discussed previously, what is this in this state? And of course, the state is not just going to be x1 and x2. Adlan will describe a bit in a lot more detail what the state is. It is going to be a couple of parameters which relate to the angle of the car and some relative parameters, what the sensors are reading, and so on. So there's going to be more parameters than that to describe the state, but nevertheless, it's going to be a vector of values. It's going to go through a neural network, and then on the output, you're going to have some Q values. Again, there will be a different, depending on this environment, there can be a different number of actions, possible actions, but we're just going to, for simplicity's sake, leave it at 4, just for us to be able to understand a bit better what's going on here. So in this case, the question is so far, what is this input into this neural network? Or more specifically, how often do we trigger this neural network? How often does this neural network go through? Well, every time the car ends up in a new state. So the car makes a move, it ends up in a new state, and then all that data, all that information from about the state goes through the network. Q values are calculated. This error is calculated based on what we discussed in previous tutorials. This error is back propagated through the network, weights are updated, then the car selects which action it wants to take, makes that move, ends up in a new state. In the new state, everything starts over again. And so basically this happens every time the car is in a new state. Well, have a look at this example. I specifically took this screenshot because it's very well illustrates the problem that is addressed through experience replay. And experience replay is not just something that we use in this course or in this specific problem. It is something that you will see used throughout, like on and over again in artificial intelligence algorithms, because it is so powerful and it's so important. So look at this car. This car in this problem or in this environment, its goal is to go from here to here and back. Its goal is to navigate its way here without crossing these walls, which are made of sand. And so the car started over here, it went down, and like its reward is based on how close it is to its target. So the car went from here, it went down, and kept going like this, along this wall. And what it's going to do next is going to turn, is going to keep going. Well, what we want it to do is keep going here. But let's think about it for a second. Once it got to this wall, every single time it moves forward, and so on, it moves forward. So there might be, like, depending on the structure environment, it could be like 100 moves here or 50 moves here. It just keeps moving forward. And nothing changes. Nothing really changes. Yes, it gets further away from this target, closer to this target. That's lovely. But in terms of the surrounding environment, not many things are changing. It's still that same wall. If you're sitting in the car, you've probably seen this situation. When you're driving and the whatever you're seeing is like the environment is so monotonous that you're just seeing kind of the same thing is just passing by. But imagine you're driving through a desert and you're just seeing the same thing. It's the same sand. Nothing is happening. Nothing is changing. And so but every single time we're putting that new state into here. Yes, of course, something might be changing. For instance, you're driving the car and your GPS is showing you're closer to your destination. So one of these inputs is changing. But a lot of these other inputs, the sensors, for instance, which are on the car, they're not changing. And therefore, as you're driving, so in this state, you input the inputs into your neural network here, 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 and here, and here. All the time, the inputs are pretty much the same. And so if you keep inputting the same inputs, the same values, the same vector, or very similar vectors into your network, because there is no variety, the car will learn very well one thing. It'll learn very well how to drive along this wall, which is on its right. And so that's how the network will update, and it will get rewarded. It will slowly start getting rewarded for driving so well. It will be like, oh, okay, so from here it'll be start learning. Oh, I'm doing so good. I'm doing even better. I'm doing it better. It will have this false perception that it's actually doing very well, even though it only learned how to drive along this wall. And so the neural network will become very adapted to driving along this wall, and then all of a sudden there's this curve and the car doesn't know what to do. And it completely doesn't fit in with this neural network. And even if it does adjust somehow, let's hypothetically say it passes this part and then it ends up on this wall, same thing is going to happen. It's going to drive from here, here, here. Okay, now the neural network is restructuring itself to adapt to this wall. And then bam, this thing happens. And then even if somehow it gets past that, it'll drive past this thing. And then same thing along these lines. So basically, it's like a very vivid example of a problem that what we have is that because the way we're using the neural network, updating it with every single state, once we have lots of consecutive states, they don't even have to be the same, but there is in environments, it's normal that consecutive states are somehow correlated or somehow interdependent. And we don't want that interdependency to bias our network. We don't want the car to just learn how to drive along like a straight line or along a curved line or like anything that you think that you can think of in life where an agent would be navigating an environment, wherever you can think of correlated or interdependent states that come after another, that can really mess up your neural network if you're just going to let the agent learn from that. And that's where experience replay comes in. What happens in experience replay is these experiences, so these states that it's in, 1, 2, 3, however many, 50 states here in a row, they don't get put through the network right away. They're actually saved into memory of the agent. And so, for instance, it saves all these, and at some point, once it reaches a certain threshold, which you'll be able to code, and Adlan will show you how to do that, once it reaches a certain threshold, then the agent decides for itself, okay, it's time to learn. I have this batch of experiences that I have, and now I'm going to learn from that batch. And so it randomly selects a uniformly distributed, and uniformly is important here because that's something we'll talk about on the next slide. We'll mention that, but it takes a uniformly distributed sample. So basically all experiences are considered to be equal. It takes a uniformly distributed sample from that batch of experiences that it has, and then it goes through them and it learns from them. So it doesn't take all the experiences, it just takes a uniformly distributed sample. So it might take a couple from here, a couple from here, a couple from here, and each experience is characterized by the state it was in, the action that it took, the state it ended up in, and the reward it achieved through that action in that specific state. So 4 elements in each experience: state 1, action, state 2, and reward. And so it takes all those experiences and then it passes them through the network and it learns. And that way it breaks the pattern of that bias which comes from the sequential nature of the experiences if you were to put them through the network one after the other. So that's the main focus of experience replay. That's what the problem it addresses. And another benefit of experience replay is that sometimes in an environment like this, you might have very valuable, rare experiences. So, for instance, I don't know, let's look at this corner, right? This is a right corner right? And a very sharp one. How many sharp, so it'll be coming from here, assuming it's going to be hugging this corner. So how many sharp right corners do we have in this whole environment? We only have one right corner here and one right corner here, right? So when it's coming this way, that's a right corner. And then when it's going back, it's a sharp right corner here. So, and this one's not sharp, this one is sharp. So there's only one opportunity in the whole environment to learn from a sharp right corner. And that's an important experience, because it might get really good at driving along straight lines, get really good at doing like soft corners like that, but, and then it will keep messing up this sharp right corner simply because it doesn't have that much opportunity to learn from it, and so therefore it will learn everything else pretty quickly, but it'll take a long time to learn this right corner. It's a very simplified example. It's a very simplified explanation, but it illustrates the concept that sometimes there are rare experiences which can be valuable. And if you're just doing a simple neural network where you're putting in your values here, and they're going through, and like, even if we forget about that problem of the sequential nature of experiences and how they can be interdependent or correlated, even if we forget about that for a second, what happens is once you put an experience in, it goes through, the network's updated, then you instantly forget about that experience, you move on to the next one. That's just how the neural network works. Then you move on to the next state, the next state, the next state, the next experience, and so on. So this right corner, as soon as it goes through the network, it's gone, and you don't have any memory of that valuable experience. Whereas with experience replay, because you're putting these experiences into batches, you can organize your batch as a rolling window. So for instance, you could have like 100 batches, so 100 experiences in your batch. So when it's coming back from here, it's as soon as it has this recorded this experience in its batch, then like at some point it takes a uniform distribution from its batch of experiences, and then there's a rolling window. So it forgets these experiences, but then it keeps these experiences. And then again, it learns from, once it's here, it learns from this batch. And then once it's here, it forgets all the way up to here, but then it has a batch of experiences like that. So therefore, now it learns from these experiences. And that way, what you're getting is that this right-hand corner, it might come up several times in its learning process, because it was in that batch when the batch was like this, around there, then it was in the batch here, in the batch here. So it came up in several batches, because a batch might be updated as a rolling window of experiences. So the older experiences get kicked out, the newer experiences are added, and then again, older experiences get kicked out. So an experience it stays in the batch for quite some time, and the car or agent can learn from that experience several times. So that's another advantage of experience replay. And of course, the final advantage is experience replay gives you an opportunity to learn from more experiences than if you're just learning from one at a time, because you have that batch, and therefore, and it's a rolling window, and therefore, even if your environment is limited to experience, your experience replay approach can help you learn faster. And instead of just redoing the environment many times, you can learn faster because you don't have to redo it. You have those experiences saved. So those are the main advantages of experience replay. Let's recap on them. We've got we're breaking the pattern of independence and correlation of sequential experiences. We save rare experiences which might be important, and therefore we can learn from them more often. And we can learn in environments. We can learn faster in environments which are experience, which have a shortage of experiences, or which don't have that many experiences that the agent goes through, and still we can be able to learn them. So that is what experience replay is all about. If you'd like to read a bit more, then there's an interesting article published by DeepMind in 2016. It's called Prioritized Experience Replay, and it talks about why are we using a uniform distribution to select our experiences from the experience batch? Why don't we find a better way to select our experiences and prioritize some of the experiences which we feel that are important? And so it's quite an interesting thing. So in this case, you will be able to not only reinforce your knowledge on experience replay, but you'll actually be able to move with the cutting edge of technology. So this is 2016 and published by DeepMind. So it's a very recent, very powerful paper. So you'll be able to actually explore the limits, or explore even further this algorithm and take it to the next level. So I'll leave it up to you to find out why and how we can change the uniform distribution to a different approach to experience replay from this paper if you'd like. And I hope you enjoyed today's tutorial, and now we know what experience replay is, and we can confidently use it in our practical tutorials. And I look forward to seeing you next time. Until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. I hope you're enjoying the course so far, and today we're talking about action selection policies. All right, let's dive straight into it. Previously, we talked about adding a neural network to our simple Q learning, and so far we're getting quite into deep Q learning. We've talked about the learning part quite a bit, including adding some elements to it, and today we're talking about this part. We're talking about the acting. So let's have a look. So here we've got what we discussed about the acting, that once you input the values, the parameters or the vector describing the state the agent is currently in that environment, then that is after all the learning is done, or even before the learning is done, basically we get all the Q values. So we're not interested in the learning right now, we're interested in the acting. So once we have these Q values, how do we understand which one we need to use? Well, if you think about it, Q values are simply, these are the predictions for the Q values. So as we did in the simple Q learning algorithm, what did we do? We just selected the one with the highest Q value. Once we have the one with the highest Q value, we just take that action because it just brings us the highest Q value, and that we know that Q value is calculated as the immediate reward that we expect to receive plus the decay factor times the value of the next state, and it's a recursive calculation. So why not? Why wouldn't you take the best Q value, and that's kind of the end of it. But as you can see here, it's not as simple. Here we're using a Softmax function, and this is where we're going to talk about action selection policies. So here, in reality, we don't have to have just a Softmax function. We can have different action selection policies. For example, we've got epsilon greedy, epsilon soft, and we've got the Softmax. And those are kind of like the most commonly used action selection policies. Of course, there are others. For instance, the most basic one is, here's a very simple action selection policy. Just select the best, the one with the highest Q value. But why doesn't that action policy fly? And why do we have different types of action selection policies? Well, it all boils down to exploration versus exploitation. And that is the core of reinforcement learning, because we've already talked about this a little bit, that your agent, when it's operating in an environment, it might predict certain Q values, which might be good, and it might not turn out great. It might turn out that those Q values are bad, and it'll be forced to explore. So if we, for instance, in this case, predict that Q2 is the best one, and then it takes Q2, takes action 2, and so from here it takes action 2, and then it gets a very negative reward. Then the environment is forcing the agent to go and explore, because now it's going to learn that, oh, actually, I thought Q2 is going to be very good, but it turned out very bad. So the result turned out very bad. So the network's going to update itself. So next time he's in this state, he might still choose Q2 if it was, if it was very, very favorable. So you might think that's like, he might need a couple of penalties, punishments in order to learn that Q2 is a bad action. But maybe he'll already soon learn that, okay, I'm going to take a different action. I'm going to take this action because now it has the best Q value. So sometimes the environment forces the agent to take to explore different actions. But sometimes the agent might find itself stuck in a local maximum. It might find that it found, like through its initial exploration, it found that, oh, this is a pretty cool action. Like, I'm going to go right here. And that's a pretty cool action. But the problem is that it thinks it's the best action simply because it hasn't explored. It's explored going up, it's explored going left, it's explored going right, but it hasn't explored going down from that specific state that it's in. And now that it's kind of like biased towards this action, it thinks it's a good action, it's going to keep taking, it's going to keep taking this action, it's going to keep getting a good reward. But what if this action would have been even better? If this action would have been so much better that if it knew about this action, it would actually switch to this action. But because it got stuck in a local maximum and is getting these good rewards, it's just going to be reinforced. It's just going to keep reinforcing itself or the environment is going to reinforce it that this is a good action to take, keep doing that. But the reality is that there's this other action that it hasn't found yet or hasn't even explored that would have been much better. And so what we want to do is we want to come up with an action selection policy that allows our agent not to get stuck in a local maximum. Yes, it's important to keep doing the good actions. That's the exploitation part. We want to exploit what we've found, but at the same time, we still want to explore. We never want to stop exploring. It's like in life, you never want to stop learning. You stop learning, you die. There's a saying like that when you're not growing, you're dying, or something like that. So you want to keep learning, and your agent wants to keep learning, and that's where these action selection policies come in. So we've got 3 listed here. So the first one is epsilon greedy. It's a very simple one. It sounds pretty complex in the sense that like it's got a cool name, and usually things with such cool names are complex. It's actually not. So basically what it does is it will select the one with the best Q value. And epsilon greedy, you might hear it in other places. It's just like a selection policy. So in this case, we're using it to select our out of our Q values out of our action. So you'll select the one with the highest Q value all the time, except for epsilon % of the time. So for instance, if you set epsilon to 10%, then you're going to, or 0.1, then 10% of the time, the action is going to be selected at random. So 90% of the time, you're still going to be selecting the best action based on the highest Q value, but 10% of the time is going to be selecting a random action. Uniformly, just going to be absolutely randomly taking an action. Or if you set epsilon to 0.5 or 0.05, that means that 95% of the time, the agent is going to be taking the action with the highest Q value, but 5% of the time, it's still going to be selecting a random action. So it's going to be going out there and exploring. So epsilon soft is very similar. Oh, by the way, that's kind of like why it's called epsilon greedy, because you're greedily selecting the action, the good action, except for that little epsilon % of the time. So the lower the epsilon, the more greedily you're selecting that kind of the action that is the optimal action, and the less you're leaving, less chances you're leaving for exploration. Epsilon soft is the opposite. So basically, you're selecting at random, you're selecting 1 minus epsilon % of the time. So if your epsilon is like 0.1, so 10%, then only 10% of the time you're taking this action, and 90% of the time you're selecting a random action. So very, very simple, just inverted algorithms. And Softmax is kind of like the next step from, or it's a more advanced version, I would say, of the epsilon greedy algorithm. Although they both have merit and they both have place, we're going to be using Softmax in our coding, in our practical side of things. So that's why we're going to talk in a bit more detail about Softmax. So let's have a look. So let's move on to Softmax. Hopefully it's pretty clear about epsilon greedy. It's a pretty straightforward algorithm. Select this one most of the time, except for sometimes go and explore. And now we also see why it's important to do that exploration, so that we don't end up in local maximums in our optimization process. So now we're going to talk a bit more about Softmax. There's a tutorial on Softmax at the end of the course. I think it's in Annex number 2, where we talk about the concept behind Softmax. I'm just going to refresh a little bit here. So there we're talking about convolutional neural networks. And by the way, we aren't going to be covering we're not covering convolutional neural networks in this section of the course. In this section, we're still using a vector. But in the next section of the course, when we're creating an AI to play Doom, we are going to be using convolutional neural networks. So it could be beneficial for you to look at convolutional neural networks and then take the Softmax function, or you can learn a bit more about Softmax after you take the convolutional neural networks annex of the course later on. But here's a quick refresher. So here we've got a convolutional neural network which decides whether it's a dog or a cat. So here we've got the voting process between these neurons, and this one says that it's got the features, the fluffy ears, the pointed face type of thing, and the kind of like the features, the types of eyes, the way the eyes look, all these features that belong to a dog. So it's a 95% chance that it's a dog and a 5% chance that it's a cat. But the question is, how did we get, and in that tutorial, we're talking about how did we get these values to add up to 1? Well, whatever the convolutional, or our whole neural network, so the convolutional neural network plus the fully connected layers, whatever it's spat out, whatever the values it spat out, we applied a Softmax function over here. And this is where we introduced the formula for the Softmax function. This is what it looks like. And then we got these values. And so basically that's a quick refresher. This is the formula for the softmax. What it does is it takes however many outputs you have, doesn't matter, it will take them and it will squash them all into values between 0 and 1, regardless of how big they are. Just by looking at this formula, you can see that there's a total sum at the bottom, so these values are going to be between 0 and 1, and also all these values are going to add up to 1 always. And so that's very beneficial for us, because when we're using the softmax function, what happens is we get these Q values. We select this best Q value, but in reality, what happens is these Q values that we get, they're actual numbers, right? So there's some kind of numbers. They don't have to add up to 1. They don't have to be between 0 and 1. Just some numbers. But when we apply softmax, we don't just select the best one. We actually get numbers like that. So we get numbers in the range between 0 and 1. And that also add up to 1. And so what other thing do we know that adds up to 1? Well, probabilities. We know that probabilities always have to add up to 1. So that is why we can say here we've got Q values, but here all of a sudden we've got we've got probabilities. So we can say that the likelihood of this being the best action is 90%. This being the best action is 5%, 2%, 3%, because we know the higher your Q value, the better the action. And so if we squash them to 0 to 1, then these become probabilities and we can deal with them as such. And therefore, now is when the action is selected, and that's how we come up with Q2. But if you look at it closely, this isn't a strict 100%, and these are not strict 0%. So this is a 5%, 2%, 3%. So the most natural way to apply the softmax in order to preserve exploration in the algorithm is to use these exact probabilities as how often we're going to be taking that action. So these probabilities actually represent the distribution of these actions that we're taking. So basically, softmax makes it very easy for us to come up with a way to combine exploitation and exploration. So the best action will always have the highest probability because it has the highest Q value, and therefore here we're going to use these as our distribution, and we're going to say, okay, we're going to be taking Q2 90% of the time. But 5% of the time, we're still going to be taking Q1, and 2% of the time, we're going to be taking Q3, and 3% of the time, we're going to be taking Q4. And the beauty here is also that as these values update, as the agent goes through the network more and more and more, it becomes more familiar with the environment, and therefore these updates. So this value, for instance, might become like it might ascertain that this value is actually less or this actually is higher, and so these probabilities will also change as an agent goes through. So even though here we've got Q2, nobody is to say that sometimes 5% of the time, to be more precise, we'll be selecting Q1 as the action to take. And sometimes, or action 1 will be taking action 1. Sometimes we'll be taking action 3, 2% of the time, and action 4 will be taking about 3% of the time. So every action has a chance to play in this process as long as we have enough iterations, and the agent goes through lots and lots of times through these states that they're in, and that's how any kind of deep learning algorithm works, that you want to do this many, many, many times so that you learn from experience. And therefore, as you can see here, it's a very natural transition to, we're not just randomly, like in the epsilon greedy algorithm, we're not just randomly selecting the actions, we're selecting them based on their softmax values, which makes it like has some logic behind it, not just at random 10% of the time we're selecting a random action, but there's some logic behind how we're doing it and based on the Q values that we've explored. And so that's the action selection policy that we're going to be using in this course. You're welcome to definitely check out the epsilon greedy action selection policy if you like, but we're going to be predominantly using the softmax action selection policy. And I've got an interesting reading for you. So this is called Adaptive Epsilon Greedy Exploration in Reinforcement Learning Based on Value Differences. It's a 2010 article, and it's interesting because Mike Michel, I'm not sure how to pronounce it, Michel Tokic, introduces a different type of algorithm, so an adjusted epsilon greedy algorithm, and called the VDBE algorithm, or epsilon greedy VDBE algorithm. You can see it over here. and he actually compares it to the epsilon greedy and softmax, and it's an epsilon greedy algorithm, which basically the main idea behind it is to adjust the value of epsilon depending on the state the agent is in. So if the agent is very certain about the state they're in, then epsilon should be smaller, so there should be less exploration. If the agent is uncertain, epsilon should be higher, should be more exploration. So it is a 2010 article. I'm not sure if it's if this new proposed algorithm is widely used or has been accepted in the community, or if artificial intelligence has moved kind of away from this suggestion. But nevertheless, it will definitely help you reinforce your knowledge about action selection policies, which we discussed. The epsilon greedy and the softmax will help you. It'll give you an opportunity to compare them side by side and also see in which direction people actually think when they want to improve artificial intelligence. So if you're ever planning on creating really interesting algorithms that are pushing the edge of artificial intelligence and pushing the envelope in this space, then this could be a good way for you to see in which direction people think sometimes when they're trying to improve the norms of artificial intelligence, or the norms that existed back then in 2010. So there we go. Hopefully you enjoyed today's tutorial about the action selection policies. We learned about epsilon greedy, epsilon soft, and the softmax. And now you're even more prepared for the practical side of things. And on that note, I look forward to seeing you next time. And until then, enjoy AI.